Hello, let's talk about generative AI applications and why you should be backing yours with a knowledge graph. As you're already well aware, generative AI and large language models are brilliant yet have several flaws, including hallucinations, lack of explainability, and lack of domain knowledge that present challenges when applying to real-world use cases. A standard approach to help solve this problem that's been emerging is known as retrieval augmented generation, or RAG for short. In this approach, instead of the user interacting with the LLM in isolation out of the box, we direct the LLM to retrieve data from some validated external source and use that to provide an enriched response. In doing so, we hope to reduce hallucination and improve explainability and traceability of the response. When you use RAG with a knowledge graph, as we'll see here in our demo, you can better surface the context of your source data, which will improve the relevance and quality of the response, as well as offer much deeper explainability. To demonstrate, consider a financial services use case where we want to use an LLM to answer questions about asset managers and company information. We're going to use two sources to build our knowledge graph, both from the United States Security and Exchange Commission, or SEC. The first source will be company 10K filings, which contain unstructured text data about the company outlook, risk of business, and other accounting details. For the second source, we will use Form 13 filing data, which contains information about how different asset managers own equity and liabilities in various companies. So as an example, Apple could file a 10K, and that stock can be owned by another asset manager like Vanguard, State Street, or BlackRock. An important thing to note about this data is that it's a mix between unstructured, semi-structured, and structured information. This often occurs in real-world use cases when looking for data to back a large language model, and it's something that Knowledge Graph, and specifically Neo4j, supports extremely well when compared to other solutions for RAG on the market. To build our Knowledge Graph, we need to structure this information as nodes and relationships. For 10K filings, we accomplish this by creating a document node, each document node corresponding to a chunk of text from a 10K filing. We will leverage an embedding model from a GenAI service to create vectors for each of these document nodes. This will enable vector search later on. For the Form 13s, we will use Cypher templates to ingest those in a structured way, creating a company node, a manager node, and an owns relationship in between, as well as connecting back to the document. In our demo application, we also include an alternative way to ingest Form 13s that uses named entity recognition by leveraging a large language model from a GenAI service provider. This is a more robust way to ingest filings that can better manage malformed, inconsistent, or semi-structured XML. So with that context, let's take a look at our sample GenAI app powered by Neo4j. Consider a question: which asset managers are most vulnerable to a lithium shortage? We can run both a vector-powered RAG with just using the vector index, as you'd see with a vector database, and also a vector plus graph approach with the graph, traversal, and pattern matching technology in Neo4j on top of a vector index. And what we'll see in the vector-only approach is that while we get a general answer around the types of asset managers that might be vulnerable, we lack a specific list because we're missing the context around which asset managers own which companies. If we go over to the vector plus graph approach, we'll see we'll get a specific list of asset managers back, along with an explanation around their position in a company that is particularly susceptible to a lithium shortage. And this demonstrates the major power of combining both the implicit facts inside of vector search and inside of text and unstructured data, and the explicit facts symbolically represented in a knowledge graph to provide the most relevant answer. To better see exactly how this works, let's take a look inside of Neo4j itself. In Neo4j browser, we can enter the query that was used for retrieval in the vector plus graph approach. This is using Cypher, Neo4j's graph query language. This query accomplishes a few key things. First, it takes the user prompt and leverages a generative AI service to create a query vector embedding. In this case, we're using Amazon Bedrock, but you can use other GenAI providers here too, including OpenAI, Google Vertex AI, Microsoft Azure OpenAI, and others. Once the query vector is obtained, We're able to do vector search on the documents inside of our graph. And then we take the documents with the highest scoring match, and we look for a graph pattern that connects the documents to the companies that filed them to the investment managers that own those companies. In this case, we're artificially limiting the results to 10 for visibility. Once we get the results back, we'll see this one document in particular that scored the highest in the vector search match. If we look at the text for that document, we'll see a lot of discussion around battery technology, which explains the high semantic match. Then with the graph pattern, we see the company that filed this document, this 10K document, which is Stanley Black & Decker Incorporated, as well as the different managers that hold a position in that company. It is through this subgraph structure that was extracted from the greater knowledge graph that allowed us to answer the user prompt with more specificity and relevance. An added benefit of using this approach is explainability and traceability. Because these ownership relationships and these filing relationships are captured as explicit relationships in the graph, it is very easy to trace back where the information came from and visualize it for multiple stakeholders as needed. We can take this a step further as well. We offer graph data science capabilities along with advanced cipher pattern matching. We can begin to understand similarities and patterns in how the LLM is pulling data over time, along with the quality of that data. And if we combine it with LLM responses and how our users interact with those responses, we can gain an idea into communities and groups of information that is very high quality versus other places in our data where you're going to need to iterate and improve on data quality, reduce duplicates, and overall improve your generative AI application over time. Through all of these capabilities, Neo4j unifies vector search, knowledge graph, and data science to improve RAG quality and effectiveness. We demonstrated today how data can be easily imported into Neo4j and used in an application to back an LLM to improve both the relevancy, accuracy, and explainability of responses, and how all these tools can be made available to your developer teams to get started quickly and create your next generative AI breakthrough. Thank you for your time.